Hello. So today we're going to be looking at something called Bernoulli Trials, which is really just it's a name for the success or failure of independent events over multiple experiments. So we're going to have a particular experiment, and the experiment on any given try will either succeed or fail, and we're going to look at the probability of having a particular number of successes and a particular number of failures. So we've already done questions like this, but this formula helps us when the questions start to get a little bit more cumbersome or annoying. So the formula is the probability of having a particular number of successes or number of successes in n number of trials or experiments. And a trial would be something like rolling a dice, and a success might be getting a 2 as an outcome. So how many 2s do you get on a die when you roll the dice 10 times? So that's what our n and our r mean. So we recognize this notation as choose notation. So we're going to have number of trials choose the number of successes we want. So this is our choice, our combinations notation. P stands for the probability of success. R is our number of successes. So probability of success to the power of number of successes. Q is the probability of failure. So we either succeed or we fail in our Bernoulli trials. And we have effectively the number of failures we're looking for. The total number of experiments minus the number of successes is going to be the number of failures we're expecting to have. Now this formula, roughly speaking, is on page 33 in your log tables. Technically the formula in your log tables doesn't refer exactly to what we're doing here, but it's very, very closely connected, and it's called a binomial distribution in your log tables. However, I advise you to just learn the formula. You're going to need it. So you may as well know it off by heart. And as I say, you won't find the word Bernoulli trial in your log tables, so you'll have to remember that it's a binomial distribution in order to be able to find it in the log tables. Now, to talk this through in practical terms, we're going to have a look at question 8 on page 210. So in question 8 on page 210, find the probability that in 5 throws of a fair dice, a 3 will occur on no occasions. Well, first of all, I'm going to pretend like we don't know this formula, and I'm going to remind you of how it is we would do this problem without the formula, and hopefully fairly quickly you'll see why it is the formula can save us a lot of time. So again, anytime we're doing this, we're going to write down our formula. So probability of or successes in n trials is going to be equal to n choose or on the probability of p to the power of or by the probability of q to the power of n minus or. Or is our number of successes, p is our probability of successes, q is our number of failures, n minus or is going to give us our number of failures. Q is probability of failure. Now, let's have a look at question or part 1. So what's the probability of getting no 3s? Well, how could we get no 3s? That would, when we are running our experiment 5 times, we'd have to get no 3 the first time, no 3 the second time, no 3 the third time, no 3 the fourth time, no 3 the 5th time. So we'd have to get no 3s every single time. So that's the only way that that can happen. So this isn't too bad. We could do this question out without using a Bernoulli trial if we really wanted to. But you'll see the advantage of the Bernoulli trial in a moment, of this formula in a moment. Now, I need to define my success and my failure. So I've done it a little bit loosely here. Let's define it very concretely. So I either get a 3, that's going to be my success, and that would be getting a 3 on a die would be a probability of 1 out of 6. So my probability of not getting a 3, which I'm going to call n, is going to be 5 out of 6. Hopefully we're all alright with that at this point. So this is just rolling a dice. Same probabilities that we've been doing for ages. And how do we get probability of not a 3 5 times? Well, it's going to be probability of n, 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 and n would be 5 out of 6 by 5 out of 6. We want to get no 6 and no 6. Sorry. No 3 and no 3 and no 3 and no 3 and no 3. 1, 2, 3, 4, 5. So we can see that when we multiply that together, we'd have 5 5s multiplied together and 5 6s multiplied together. So the short way of writing that is going to be 5 to the power of 5 all over 6 to the power of 5. And we put that in our calculator, we get 3125 all over 7776. This is how we would do that question without a Bernoulli trial. Now, let's see if it's a bit faster if we use the Bernoulli trial. Well, we have, what are our different parts to our formula? We want to define n and or. N is going to be our number of trials. We're rolling the dice 5 times, so that's going to be 5. Or is our number of successes. Success is getting a 3. We're interested in where we don't get any 3s. P is going to be the probability of success. That is going to be probability of getting a 3, which is going to be a 6th. And the probability of failing to get a 3 is going to be 5 out of 6. I've now defined all of my different terms for my probability. So P of no 3s is going to be 5, choose 0, multiplied by a 6th to the power of 0, multiplied by 5 sixths to the power of 5 minus 0. I put that into my calculator and I will get exactly the same thing out. You can see it fairly straightforwardly here. This is 1, this is 1, and this is 5 over 6 to the power of 5. So we end up with the same thing as we had up here. So we end up with the same answer. So you can see that these two different methods, this is how we would have done the question up until today. This is our Bernoulli trial formula. And we can see that we get the same answer. Now that one's fairly straightforward. Part 2 would be much longer to do out completely. So I'm going to do a slightly abbreviated version of the way that we would have done part 2 in the past. So the probability of getting 1 3 is what we're asked for. So what are the different ways of getting 1 3? Well, we could get a 3 the first time, not a 3, not a 3, not a 3, not a 3. Or we could get not a 3 and then a 3 and then not a 3, not a 3, not a 3. Or you can see where this is going. We have not a 3 and then not a 3. I'm listing out all of the different ways that I could get 1 3, and all of these meet my criteria, so I would have to work them all out individually. And add them up. So this or this or this or this or not a 3, not a 3, not a 3, not a 3, and then get a 3 on my 5th roll of the die. I'd have to add up all of these different outcomes. Well, I can see here that I'm going to have probability of 1/6 multiplied by probability of 5/6 multiplied by itself 4 times. So each of these is going to be a 6th multiplied by 6 to the power of 4, and I have 1, 2, 3, 4, 5 ones of them. So probability of 1, 3 would be 5, because there's 5 of these, of 1/6 by 5/6 to the power of 4. When we put that into our calculator, we will get 3,000. Oh yeah, it works out as being the same as from part 1, but there isn't any significance to the fact that they're the same. It's just a coincidence. Now, the other way of doing this would be to simply use the Bernoulli theorem. So probability of 1, 3. We'd have n is 5, or is 1, p is 1/6, q is 5/6. Subbing into our formula, we'd have 5 choose 1 on 1/6 to the power of 1, 5/6 to the power of 5 minus 1. We put that into our calculator and we get exactly the same thing. Final part. I am not going to do this out the long way as it gets to be a lot of writing out. So if we want the probability of getting 2 3s, hopefully you are satisfied that the method we've been using so far and our Bernoulli trial are equivalent to each other. And for that we have n is still 5, this time or is going to be equal to 2, p is still 1/6, q is still 5/6. So probability of getting 2 3s is going to be 5 choose 2 on 1/6 to the power of 2 for 2 successes, and 5/6 power of 5 minus 2. We put that into our calculator and we get 625 all over 3888. Now, that's how we use our formula. The critical thing for Bernoulli trials is they only work for independent events. It is extremely important that we only attempt to use Bernoulli trials when we are talking about independent events. But if we can keep that in mind, you can see they can be a very useful tool for saving us an awful lot of time. If we have independent events and we're running an experiment multiple times and we have a success or a failure, then this can be an excellent tool for saving time in the exam, and it's a formula you're required to know. They can ask you specific questions about the Bernoulli trial. And that's what we need for now.